In this video we'll continue assembling the Curta calculator, and the next step is to insert the input register gears. And one of the key things to getting a machine like this to work, as I mentioned in the first video in this series, is getting friction as low as possible. So all the parts might work fine when they're independent and there's just one, but when you start trying to move lots of different parts of the machine at the same time, all the small frictions add up and it can become extremely difficult for the machine to function the way it should, or parts might even start breaking. So I mentioned I'm not a big fan of using silicone oil or grease in a machine like this for several reasons. Firstly, the Curta is fairly open. There are big open slides and gaps in the outer casing, so you get dust and debris going into it. Also, with PLA that we're using for the 3D printing, it does tend to shed small particles over time, and if you're using grease or oil, they will build up, get inside slides and whatever else, and ultimately it will stop working. It will start to seize up. Oil and grease is fine for things like open gears, but where you have slides and the like, it's not really a good solution. So I thought I'd demonstrate the method I normally use when using PLA. Haven't built a Curta before, but I've built lots of fairly complex devices using 3D printed parts, and there's a general method I use that seems to work quite well. So I thought I'd just quickly demonstrate this before we start any further assembly. So what we have next are these shafts. Now I have already kind of taken them to fairly close to their final size, but what I have to do now is to get them to work well with the gears and the various slides and pieces that they'll be running in and with. And if I don't do that, the machine almost certainly won't work properly. Now, if I demonstrate this one that I've done already, what you can see is that although there's no real play in this, it's extremely free to move, and this is what you need. It's really getting to the point where the parts will move almost like there's no friction between them, but without lots of free play. If you have lots of free play, again, the machine probably won't work because it won't be moving the parts that are meant to be moved in the way they should be. So the way I go about doing this is we start with, this is one I haven't done yet, we start with the part that's already been taken fairly close to the final size, and if we try fitting one of the gears to it, it should go in, but it's not stiff, but it's not free to slide, and this, although it might work, it's not going to work particularly well. So what I'd start off by doing is putting the shaft in a hand drill. It's very light, I don't want to damage it. And then taking some 800 grit emery cloth and then just very carefully cleaning up the surface. Doesn't take much. This isn't really going to change the size all that much, it's just going to kind of condition and prepare the surface finish. So it's not going to make the shaft much smaller unless you do it for a long time. Once I've done that, I'll take some 2500 grade paper. It's now starting to feel quite smooth. We'll try fitting the gear onto it, and what I'm looking for is for the gear to slide up and down the drive shaft without there being any appreciable stiction. So we're trying to get rid of all the tight spots. Now the thing with lubricants, it's not meant to overcome parts that don't fit together properly, it's just meant to allow them to slide freely past each other. So you can now see that this is now sliding all the way up and down. It doesn't stick till we get to the bottom bit that we haven't done yet. So we pop the shaft out, spin it round, and do the same thing on the other end. So we'll start again with the 800. The and onto the 2500. I normally take a bit more time than this, but for the sake of the video I'm trying to speed things along a bit. Okay, so once that's done, we'll test fit the gear again. And now this does slide all the way up and down quite nice and smoothly. Still feels fairly rough though. Now, if you've ever built something like a clock, so one of the things I tend to build, I've never videoed it, but I make large clocks out of brass and raw materials. So one of the steps in clockmaking is when you're trying to get a bearing to run really freely, and again in clocks friction is the enemy. You do everything you can to minimize it. You go through a process called burnishing, which is basically rubbing a smooth surface against the bearing surface you're trying to clean up. Now, I've tried this quite a few times and it works extremely well with PLA. So on here, if you were to zoom in with the microscope, there'd be little undulations and high spots and low spots. And what you can do is burnish that. So you'd start by making sure it's nice and clean. You don't want any grit left over from the emery cloth. And you basically move this back and forth at fairly high speed. And what it will do is the local areas where there's a high spot or a low spot, the PLA will tend to melt. It's only very localized, it's just very small particles, and it will tidy it and clean up the surface. And I can't really demonstrate this on camera, but if you try this, you'll feel that suddenly, as it has done now, it goes really smooth. So it's now gone from feeling fairly rough to this is now feeling quite nice and smooth. We'll do the same thing at the other end. And I'm putting a slight twist on this as well to put a bit of pressure on the gear. Not going too hard, I don't want to snap the shaft or anything. It's mainly the speed of the motion that's important. It doesn't need to be a lot of pressure. And you keep going until that rough feeling has gone away. Now, this won't work if the part isn't already fairly smooth. It needs to be fairly close to its final state. And so once we've done that, you can see we've now got a very nice, clean, smooth shaft. So the next thing is we clean this off. So we take a bit of towel, make sure we've got all the debris off it for the final step. And the final step, for me at least, is to coat this in this, which is dry PTFE. I'm not going to do it just yet because I need to glue the gear onto the end of it, and if I obviously put the PTFE on, then the glue's not going to stick very well. I've got one here that's already glued but not lubricated, and this stuff, you just shake the can, especially extremely small PTFE particles in a carrier, and all you do is just spray this on. One thing, if you are using this, some people have said this is useless stuff, it doesn't lubricate, and what they've been doing is assembling the parts first and then trying to squirt this stuff down into the gap like you would with oil. You can't do that with this lubricant. You have to coat the surface. So it'll come out wet, but it will very quickly dry off. So what I'm doing is just putting a fairly light coat on, make sure it's completely covered. And then you can either wait until it's fully dried, or if you want to coat the inside of the gear as well, which is probably a good idea, is try and get some of the PTFE into there. Slide it up and down. Initially it might feel fairly sticky until the fluid disappears. Make sure it's well distributed, and after a few seconds the carrier that's in the lubricant will evaporate. And you'll feel it starting to slide much more freely. You'll see it's also gone darker, and what the lubricant does, it kind of puts a PTFE coating on the outside of the part, and it's very good in terms of hard wearing. It won't just rub off or wear away. It seems to be incorporated into the surface of the material, and it also is dry, so it doesn't attract dirt or dust, and this actually now feels like a piece of PTFE. And this in terms of friction is now extremely low. It hasn't finished drying yet, but the way this feels now, it feels extremely smooth. There's no sort of stiction or hard spots or sticky areas, and this now is exactly what you want. We don't have any real free play or too much slack, but this now slides in and out of this extremely well. And when it's completely dried, just move it in out a few times just to finish cleaning up the surface, and this now is exactly what we need for our calculator to work exactly the way it's supposed to. So the lubricant hasn't quite dried yet, it's still a little bit sticky, but almost there. So you can see how free moving that is. There's almost no resistance, and in fact I can't really feel any resistance to this moving at all, and it will stay like that for a long time. It's not going to, like grease, it's not going to attract dirt and dust, it's not going to dry out, it's not going to run down and pool in the bottom of the machine. And so as I say, this stuff, you can get other brands of this. This is the one I tend to use, but it works in machines like this extremely well as long as you apply it properly. Don't, as I say, don't try and squirt it down into the gaps. That won't work. You need to properly coat the entire area that you want to do. So I'm going to do that with the shafts as we proceed. I'm not going to prepare them all first. So the next step is we'll get the part of the machine we've already assembled back onto the bench, and we'll start to put the gears in place. I'll also try to explain how the calculator works, at least the basic operation of it, in case you're not familiar with the way mechanical calculators operate. I've prepared some of the shafts, trimmed them up, polished them, lubricated them, and checked that the gears fit correctly. And I'll do the rest later, but before I go any further with the assembly, I thought it would be a good idea to just very briefly explain how the calculator works. So what I've done is install one column into the calculator. I thought it would be easier explaining it like this rather than trying to explain it when the entire thing's assembled. Partly because we can see the internals more clearly when it's assembled with just one column, and also it will make the explanation a lot easier. So I was trying to figure out where to start with the explanation. Now if you know how mechanical calculators work, then you probably already know exactly how this functions. But I'll try and explain this as clearly as I can. I'm going to oversimplify the explanation, and I'll go into the higher functions when we get more of the machine assembled, but for now we'll just stick to the basics. So the Curta calculator can do addition, subtraction, multiplication and division, but in fact all it can do is add. It might sound a bit weird, but it provides the rest of the functions through a very clever and elegant sequence of events that it performs as part of its operation, and I'll go through those, as I say, as we get more of the machine assembled. What I want to do just now is explain basically how the adding works. So the Curta has three what we might refer to as registers. It's got an 8-digit input register, which is what these do. There's normally 8 of these, and these allow us to set a value that we want to input into the calculator. At the top there will be a carriage that sits on here, and that carriage contains 2 more registers. It contains the output register, which is an 11-bit register, or 11-digit register I should say, and it contains a counter register which is a 6-digit register. So those 3 registers all kind of work together, but I'll just briefly explain what the calculator does with the numbers. So if we go back to primary school and look at the way that addition works, and then I'll explain how this is performed in the calculator itself. So if we take 2 numbers, doesn't matter what they are, just random numbers, so we'll start with 110, and to that we want to add, for the sake of argument, let's say 91, and there's also an implicit 0 here. So it doesn't really matter which of the registers these are in, whether it's this is the input register or this is the input register and the other one's the output register. But one of the two registers will contain the top number and the other register will contain the bottom number. So for argument's sake, let's say that the top number is already present in the output register. That's the register that would normally be in the carriage, and the bottom number is in the input register. That's the number that we select with these sliding selectors on the side of the calculator. So to add these numbers together, the calculator processes the columns one at a time. In this case it starts with the first column, the units column. So it will start here, and what it will do is it will add these two together, and I'll show how it does that in a minute. But it's going to add 1 and 0, and that will give us a result of 1. So the first column will end up as a 1, which means that in the results register we'll end up with a value of 1, 1, 1. So it's now going to move on and process the second column, and in this case it's incidentally in the first column there's no carry, so there's no other numbers to add, it's just these two. In the second column it's going to add a 9 to a 1, and because this is decimal, the maximum biggest digit it can store is a 9, so this will result in a 0 in that column. But it will also produce a carry, so we'll have a 0 plus a carry, and that means that what we end up with in the output register at this point will be 1, 0, 1. It will then move on to the third column, and it will add the 1 and the 0, so it's 1 plus 0, but it's also going to add the carry. You can think of the carry as an implicit 1, and that means that the value it's going to produce in the third column is going to be 2. So it's 1 plus 0 plus 1 is 2, which means that in the output register we end up with a value of 2, 0, 1. And if we look at the numbers we fed in, 110 plus 91 is indeed 201. So the question is, how does the calculator actually do this processing? So if we get the calculator, then the input register's value, that's in this case the bottom number, is set using the slides. So if for example we set a 5, then what will happen is this shaft will advance the count by 5, and the count's advanced through this gear. So this gear will normally mesh with the we've got the moving part of the calculator, which is the carriage that sits at the top, and I'll explain in a future video why it has to move. But assuming that digit 1 is aligned with column 1, then as this gear turns it will advance the value in the output register. If we set this to 5, it will do that 5 times, so if the value was 0 it will advance it to 5, if the value was 1 it will advance it to 6, etc. So all it does is it just advances the column value. So what I'll do now is I'll take this part out of the way and we can start looking at how it handles the carries. So I just need to get this removed. So if he wants to carry a number, that's where this drum comes in, and there are two registers at the top, as I said. There's the counter register and the output register. So there are two of what I'm about to describe. One you can't really see, it's further up, but the one for the these are the levers that extend all the way down, and the other levers, if I get one of these shorter ones, you can see that it's got a tab higher up, and that fits through this gap, and it meshes with the same type of mechanism we're going to look at here, but higher up. And it does that so it can handle the two registers on the carriage separately. So what happens here is this arrangement here is the carry lever, and this is responsible for moving this gear up and down the drive shaft. see the gears moving as the carry lever moves. And those gears look like this. Now there's kind of looks like there's two gears on here, but the top part is not actually a gear. What that's for is to prevent the shaft from turning, so that rides on this section of this bell here, so it will sit with that like this, and it prevents this from turning. But when it's moved down, then it comes at a certain point in rotation, it's clear of this disc here, and it allows the drive shaft to rotate. The bottom gear is actually a gear, and it's responsible for the carry addition. So I'll show how that works. When we rotate the machine, we've set the input value here by virtue of where we've put the slider. And if we rotate the machine, you'll see we have all these teeth on this drum. If I set it here, you'll see that as the machine goes round, it starts rotating this shaft. And the amount it rotates it by is dependent on where it is in relation to the drum. So at the top, it will set 0, it won't rotate at all, then 1, 2, 3, 4. Might look a bit odd, I'll explain this in a minute. And then as it continues to rotate, it will get to the end and it will have rotated by an amount determined by the position of this gear up and down this shaft. Now, as I said, this might look a bit strange, and the reason that the teeth, try and get into a position where you can see, hopefully you can see all this. This might look a bit odd in that the numbers kind of go down rather than up, and you probably expect them to go the other way. 0's at the top and it goes down to 9 at the bottom. I've drawn a little template here to help us explain this. If I offer this up, then in this position the first digit, when we've got 0 selected, runs in this position, and there are no teeth on the drum at that point, so it won't advance the drive shaft at all. It then comes down, and if you look at the numbers, 0 is in this clear space, 1 is actually between these teeth. I'll explain why in a few seconds. And if we bring this around, you'll see that in this position there's only one tooth that the gear is going to encounter. If we go further down, we have 2, so we have 2 teeth here, this one and this one. Further down we have 3, 1, 2, 3, down to this one, 1, 2, 3, 4. And this is where it gets a bit old. We'll set it all the way so we can see more of the drum. Notice that the spacing of these 2 teeth is exactly 1.5 of the spacing of these teeth. So in other words, at this point, when we get to 5, then the next, actually here, the next increment will take us to 6, and it will then start to be coincident with the teeth. So up here it's running through the gaps, and then here it changes over and starts to run to where the teeth are. So 6, 1, 2, 3, 4, 5, 6. Next one down is 7, 1, 2, 3, 4, 5, 6, 7. So on down to 9. So this bottom one, there are 9 teeth. So depending on where we set the slide for the input selection, it will determine how far this, so how many times this drive shaft will turn, and so how many digits will increment on the output register. I'll explain why this is like this in a few minutes when we come to subtraction. So to handle a carry, the way that the machine works is, let's say where, it doesn't really matter for the sake of demonstration, I'll just put it here. But what we have here, if you notice, there's an extra tooth up here, and if you look where it's arranged, it's kind of in the next, what would be the next row of teeth if it was on this drum. So it kind of coincides with about this position. So it's really the 10th tooth if it's used. So when we start a calculation, I'll go all the way around, we're now in the home position, we'll start a new calculation, and notice one of the first things that happens, again I'm not quite sure how clearly this is coming across on the camera, you've got this little ramp arrangement here. What it's for is, I'll start this again. If I push this down, the carry lever is in the carry position, and I'll show you how it gets there in a minute. If we go around and start a new calculation, the carry lever is in the down position, but when we start the calculation, that ramp causes the carry lever to pop back up into its no carry position. So effectively the calculator is running through each column in turn, and it's starting by clearing the carry lever in case there isn't a carry. It then goes around and it starts counting the number of teeth that are hitting these gears. Now if the previous, I'll run this all the way through before I go any further, when it gets to the end of the drum, so it gets to this point, it's going to stop rotating. So notice now it's not rotating anymore. It won't go any further because there's no carry. We do the same thing again, but if we assume that the column previous to this one produces a carry, then it will cause this to pop down. And I'll explain how this arrangement works in a future video when we look at the carriage. But for now, just take my word for it, when there's a carry in the previous column, then this carry lever will be pushed down. Pushes this gear down. So firstly that unlocks the shaft, and secondly it puts this gear in line with this. So remember there's an extra tooth on this disc here, and this gear is now in line with it. So when we get to the end of the drum, keep going around, we can see the shaft turning as it counts the teeth on this drum. Gets to the point here, which is previously where this stopped turning, but if you watch, this extra tooth is now going to turn this gear. So this drum turns this gear, and the carry tooth that's on here will turn this gear, and it will turn it one more digit. So you can see it's turning. So that tooth has turned this gear, so it's added the carry to the total because this gear is driving the output register. And then it goes around and it does that for all the columns, completes the calculation, ends up back in the home position. Notice the carry lever is still in the down or carry position. But as I said previously, when we start a new calculation, the first thing that happens is that ramp clears the carry lever. And that just ripples around all the columns in turn, adds the numbers, or creates a carry if it needs to. Okay, so that's how it adds numbers, and it works in conjunction of course with the carriage. The reason this arrangement looks a bit odd is because if we go back to this template, as I said, we were working with it here, and you can see that the first digits are running in the gaps of the drum, and the last ones are running in line with the teeth of the drum. But what we can do is move this down, and the purpose of doing that is it allows us to do subtraction. And that might sound a bit strange, but if we look at the number of teeth that are on here and we try and do a subtraction, we'll just subtract some simple numbers. Let's say we have 8 in the output register, a value of 8, and we want to subtract a value from it. So if we want to subtract 9, for example, so 8 minus 9, then that should give us a value of 9 because it's going to underflow, and again the calculator keeps track of any borrows or carries that are created. But to do this, because we can't actually subtract, what we can do instead, because it's a decimal machine, we can actually do this by adding 1. So if we add 1 to an 8, we get a 9, which is what we're looking for. And so if we have the input slider in position 9, which is the value we want to add to the output, this gear will be kind of all the way down here. So it'll be in position 9, because now remember we've moved the drum, so it will be here. Notice the position 9 is off the bottom of these teeth, but if we continue to rotate this, you'll see there's one tooth here that will cause the gear to rotate one digit position. And if we do something similar now, let's say, and that gives us the value we want, let's say we have 8 and we want to subtract 8, that should result in a value of 0. And we can do this by adding 2. So we're going to add 2 because we can't subtract, so we're going to add 2 instead. So 8 plus 1 is 9, plus 1 will result in 0 in this column. So if we put this up to the next position, which is at the moment is the gaps, if you recall, we're looking at the gaps at the moment at this side, and then we'll continue to rotate this. There are 2 teeth, 1, 2, and you'll see the gear rotate 1, 2. So we've really added 2, we haven't subtracted anything, we've added 2, but we've got the correct result of 0. And one last example, if we have 8 and we want to subtract 7, then the result should be 1. But what we can do instead of subtracting, because we can't actually subtract, is we can add 3. So that would be 8, next number's 9, 0, then 1. And that is the correct value. Just by adding 3 to 8 in a decimal column, we end up with a value of 1. And again, we run this round and get the gear in the right place. So it will be there. So in the input selection, we will have set a value here of 7, but we're not going to add or subtract 7, we're actually going to add 3. So 3 teeth, 1, 2, 3. You'll see the gear 1, 2, 3. It's added 3, but that would result in a value of 1 in the output column. Okay, so that's how it does subtraction. It just, in addition, it just adds the numbers as you'd expect, but in subtraction, it expects the numbers to overflow, so it adds different numbers. And that's why this drum looks a bit odd. It's just done to allow us to do addition normally or subtraction by creating overflows. Okay, so that's fundamentally how the calculator works. It does division and multiplication by repeating these steps. It's quite clever the way it does it. Most mechanical calculators do it the same way, incidentally, in that they move the carriage. So that it doesn't, for example, if you're multiplying 1,000 by 1,000, you don't have to crank the handle 1,000 times. You just crank it 4 times, but you move the carriage 1 column position to process each column. Okay, so the next thing to look at is we'll start assembling this. I'll show you how it goes together. I'll take it back apart and then we'll start to assemble it. One thing to note here is the addition I was talking about, these little blocks that I mentioned previously. They are here, and they are to I prefer this arrangement. It gives much better support for these bearing slides, but it also allows the system to operate with much less friction, so it kind of gives a lot of support to this. Also makes it easier to adjust when you turn the screw, because initially, the original design, the screw heads sit on the shoulder of this guide. When you turn the screw to tighten it, it moves the guide out of the way, and if you're trying to adjust it, it's a bit of a pain. It's not impossible, it's just easier this way, but the main issue is this extends down and provides support to the back of the guide, and it makes the whole thing quite rigid, and it means that the friction is much lower. And bear in mind, when this is operating, it's being pressed up from down here, not from the bottom, so you need to make sure that it works well in that mode. Now, I made the springs from 0.6mm piano wire as per the build manual, but I think it's a bit stiff. I think we can go lighter, so I'm going to try 0.4mm for those springs and see if that improves the operation, but I'll leave it as it is for now. So next thing, I'll tear this apart and we'll start to assemble it properly, but hopefully now it's given some idea as to how this works. And incidentally, we changed the modes that it runs in by moving this carriage back and forth. So if we put it in the home position, we can slide this back and forth. As ever, friction is what we're trying to avoid. So one thing that's important is to make sure that these levers don't rub on the inner part of the gear. So what I've done here is made sure that all these gears, the center section, is fairly accurately finished, and it minimizes the friction. We don't want a big gap, otherwise there's a chance these could foul on the teeth rather than cleanly sliding it. But but you don't want it rubbing on here either, otherwise it's going to create a lot of friction. Okay, so I'll get this taken out and then we'll start looking at how to fit these drive shafts into this assembly. So assembling the drive shafts into the calculator is fairly straightforward. All we have to do is make sure we select the right gears and the right shafts. They're not all the same, so make sure we get the right ones, and also make sure we fit them the right way around. So once we've got the right shaft, we'll put the first one in, and I'm following the same sequence that's shown in the manual. And all we do, I've reamed these holes out by the way, so in theory they should be the right size. So we start off with this one, feed it through from the top, and then we fit the gears onto the shaft as we fit the shaft. Obviously we can't put them on once the shaft's fully in place. So fit those on there, slide it all the way in, make sure it engages with the hole in the bearing plate. And that's the first one fitted. Make sure it spins nice and freely. If it doesn't, we'll open up the holes very slightly. This one's a little bit on the tight side, so I'm going to open up the holes very slightly. So it feels like it's the bottom hole that's tight. So I'm just going to run an adjustable reamer through this, open it up very slightly, only by a fraction of a millimetre, and see if it frees up the shaft. It's not a lot of friction, but as I said before, the more we can reduce friction at this point, the easier our lives will be in the future. It's better to spend time doing this now rather than spend hours swearing furiously at the machine because things start snapping when we try and turn the handle, or that it tells us that 1 + 1 = 37. So I'll get this fitted and we'll move on to the next one. Okay, so that's the first one fitted. Spins nice and freely. Take the next, make sure we've got the right shaft and gear combination, and then this fits into the next hole. Gear on. Engage it in the bottom hole. Make sure it spins freely. Which it does. And then move on to the next one. So I'll get the rest of these fitted. Be a few seconds for you, be a few hours for me because I need to make sure they all fit and spin freely, and then you'll see what it looks like with all these drive shafts in place. So that's all the drive shafts fitted. I've tried to make sure they're in the right order, and I've made sure that each one is free to spin, doesn't bind up, no tight spots, and that all the gears move freely on the shafts. On 3 of the shafts the gears don't move, so they're fixed, and there's no information in the manual really about permanently fixing them. So what I've done here, I mean, you could super glue them of course, but then you won't be able to get the thing apart again. So there are grooves in the shafts either side of where these gears sit, so I've used O-rings either side, quite wide grooves. There's 2 O-rings per groove, but it holds them in exactly the right position and they line up with the gear they're supposed to. I'll show that in a later video. So that's all these fitted. They all do what they're supposed to as far as I can tell, and at the moment, as you can see, they are free to move, and they would just fall out if we tip the calculator up. So the next part to fit is this retaining ring that sits around the gears and stops them lifting up. There's a shoulder on each gear, and this ring stops the gears coming up past that shoulder. Now I have polished up this ring where it touches the gears. I'll lubricate it as well before I fit it. It's held in place with 3 M3 screws. I've already tapped this part, so I'll get this fitted and we'll see how it looks. So that's the retaining disc fitted. I've checked to make sure all the gears still spin okay. A couple of tight spots, I need to check that. I think just a little bit of a rough spot on the gear, and I'll deal with that. All I'm going to do is take the disc off, slide the shaft part way out, and probably just clean up behind the shoulder of the gear. It's just in a particular spot, so I think it's just a bit of a bump on the gear itself. Not particularly tight, but I'd like to get rid of that now. Most of them seem fine. So at the moment, as you can see, all the gears are free to slide up and down. There's nothing stopping them. So in the next video we'll fit the carry levers, and then we'll look to fitting the input shaft sliders. But making good progress, it's coming together quite nicely, and so far everything moves quite freely.